Newton's third law is the most misunderstood law in physics. So let's try and see if we can get it right. So far we have discussed a number of forces. We have discussed the only long-range force we'll be looking at, gravity. When we talk about weight, that's what we're talking about. There are other forces, contact forces, tension, friction, normal forces. So when you press against something, you're exerting a contact force against it. What all these forces have in common is that they all have associated with them an agent and an object. So here these words have very specific meanings. So let's suppose we have a force, and I'm going to represent that force by this arrow. A force can't just exist like that. A force has to be acting on something. Whatever that force is acting on, we're going to call that the object. Now this force which acts on this object must have some cause, some agent that is responsible for this force. So let's suppose I have another body over here. So let's suppose these are two planets, and this is, like, say, a gravitational pull. This is a planet, and this is a moon around that planet, let's say. Well, this planet then would be the agent for this force. So here is this planet. It's pulling on this moon, and this is the force representing that pull. So I'll just call this some weight. Let's call this object A and this object B. I'll say that this is the weight acting on A caused by B. So A is the object, B is the agent. So it's object agent. What Newton's third law is saying is that this situation that we have here cannot exist. No force can exist as a single entity. If this object, and maybe I shouldn't use the word object here, if this entity is the agent of this force that acts on this object, then this object is also an agent exerting a force on this, which is then an object. So that may have been a bit confusing. The point is that forces exist in pairs. So this force can't exist by itself. There must be another force acting in the opposite direction but with the same magnitude. So what's true about these? This force is equal to the negative of this force. So these are gravitational forces. That's why I'm using W, just in case you're wondering why. So that's Newton's third law. All forces exist in pairs. These pairs are equal in magnitude but act in opposite directions. These forces are also called action-reaction pairs. Now this terminology has been misleading, and quite frankly I don't like it, but I don't have a better way of expressing this idea. These terms lead you to believe that this force comes first and this one comes afterwards. A reaction comes after the action. That is totally wrong. These forces exist simultaneously. The minute one exists, the other one exists at the same time. It's not like one force exists and then the other one exists because of that one. No, they exist at the same time. There's a famous saying, you can't touch anything without being touched. So for example, if you press against the wall, the minute you touch that wall, you're exerting a force on that wall. The minute you touch that wall, the wall is exerting a force on you. So in some books, you used to see Newton's third law enunciated as for every action there's an equal and opposite reaction. Please don't use that definition. It's not necessarily wrong, but it's totally misleading. Better is to say forces exist in pairs, equal in magnitude, opposite in direction. So for every object there is an agent, but this agent is also an object for this object, which is also an agent. So I hope this is not too confusing. So if I look at this force here, this is the agent, A is the agent and B is the object. But if I look at this force, A is now the object and B is the agent. So you need to be able to identify these action-reaction pairs. So let's look at a few examples. Here's a classic example. This person is exerting a force on the wall. So notice this is the force that this hand exerts on this wall, and this is the force that the wall exerts back on the hand. These forces exist simultaneously, so it's not like this force appears and then this one appears afterwards. These two forces are called an action-reaction pair, but you cannot say that one is the action and the other is a reaction. So that you might find that puzzling, but you can't say, well, this one is the action and this one is the reaction, or vice versa. You can't say this is the action and this is the reaction. but together they make an action-reaction pair. So if we look on this force, the hand is the agent, the wall is the object. If we look on this force, the hand is the object and the wall is the agent. These forces are equal in magnitude and act opposite in direction. Here we have an athlete pushing off, and these form an action-reaction pair. So this is the force that the surface of the ground exerts on his foot, and this is the force that the foot exerts on the ground. Note that later on when we're solving problems, we won't show the complete action-reaction pair for every force. We will only look at both of these forces if it becomes necessary to do so. So in a particular problem, I may be only interested in the force that the ground exerts on the athlete's foot, and so then I will only show this force. In some problems, they ask you to find the force that the athlete's foot, say, exerts on the ground, and what you do is you realize, well, you can find that force by finding this one, the force that the ground exerts on the foot. And so we find ourselves doing that often. We find one of these, and then that tells us the next one. Remember, these are equal and opposite, so they have the same magnitude, act in opposite directions. Here is another classic example. We have a book on a table, so let's look at the forces acting on this book. There is going to be the weight, and what other force acts on this book. This you see a space here, but consider the book to be touching the table. And then there's the normal reaction. What force is this? That's the force that the table is exerting on the book. If the book is in equilibrium, that means these forces cancel out. Question: do these forces make an action-reaction pair? If you answered yes, you would be very wrong. Remember, action-reaction pairs never act on the same body. If you have some force acting on some object, the other member of the action-reaction pair acts on the agent of this force. So in the case of this book, if we want to focus on this force, the normal reaction, we need to look for the agent of this force, and the agent of this force is the table. So that means there is a force. This book is exerting a force on the table, equal in magnitude to this, but acting in the opposite direction. So I'll just call this, say, n prime. So these two forces are equal and opposite, and these two now form your action-reaction pair. So very often in a problem, we are only interested in the forces acting on this book, for example, so we wouldn't draw this. So be careful. These two forces happen to be equal, but just because they're equal, that doesn't mean they're an action-reaction pair. So an action-reaction pair involves the agent and the object. So if we look at this weight, so the object of this force obviously is the book also. So what's the action-reaction pair for this weight? Well, we need to identify the agent. What is the agent of this force? Well, it's the earth. So if the book is being pulled by the earth, well, the book has to also pull the earth upward. So you might find this a bit strange. So if the earth is pulling on the book is pulling up on the earth. So again, in most problems you wouldn't draw this, but you need to be aware of this. So action-reaction pairs never act on the same body. Notice this force acts on this body, and the action-reaction pair acts on the other body. So action-reaction pairs involve the object and agent involved in the force. These two just happen to be equal and opposite, which is why this book is in equilibrium. These forces cancel out. Action-reaction pairs can never cancel because they never act on the same body. So I can't stress this enough. Make sure you get it. Here is another very typical situation that you'll often find in physics problems. What we have here is the moment of impact in a collision between a very heavy truck. Let's say this has a mass of 10,000 kilograms. Let's make it very massive. And this one, let's say, has a mass of 1,500 kilograms. So a very small light truck. When they collide, I think everybody would assume that this small vehicle would be damaged more severely, and I would agree. No problem there. The question is, on which was a greater force exerted? When they collide, the large truck exerts a force on the small truck. So let's call this A and this one B. So this would be the force on B due to A. And of course, this small truck exerts a force on the large one. And so let's say that's the force on A due to B. So that's a force on B due to A, a force on A due to B. Which of these is greater? You probably want to say that the force acting on the smaller truck is greater because, well, it gets more damaged in the collision. But you'd be wrong, and you know that you're wrong. These forces have to be the same. These two forces form an action-reaction pair. So very often you find questions like these in physics tests. For example, you have a truck barreling down the road and it collides with a small fly, and so you see a fly get all splattered over the windshield. And a typical question would be, well, which force was greater, the force that the fly exerted on the windshield or the force that the windshield exerted on the fly? And the answer has to be that they are equal in magnitude. Now, the force that acts on the fly has a greater effect on that fly. Likewise, in this collision, maybe this force will do more damage to this truck than this force will do to this one, but the forces are equal in magnitude. Another typical question would be, let's say a man and his daughter, so this is some adult, let's say, and playing with a child, and so there's a little child here, and so they push on each other. Which of these forces is greater? Well, they have to be the same because these two forces constitute an action-reaction pair. So that's it for this set of videos on forces and Newton's laws.